Welcome everyone to session 60. I hope you had a good lunch and you've enjoyed the conference so far. So we've got Farley here on the 102 to talk about Modernize mainframes with Red Hat OpenShift Platform, and he is also from Red Hat. So I will hand over to Farley. Yeah, thank you very much.
Thank you. So, as some of you might have imagined from the title, we'll be talking about OpenShift, and OpenShift is a container platform, as we call it. But I think it's important to see a little bit what there is behind a container platform. So let's start from the very basic containers. So obviously those are not the containers we are talking about, because it would be hard to put those kind of containers onto a mainframe or any kind of server, but still, I think it's important to start from here, because the 20 and 40 foot container started with a very clear goal, which was to make it easier to move shipping goods from one place to the other. And the reason why containers work in such a good way, in fact, now they are used pretty much everywhere into the shipping industry, is that they are very flexible, in the sense that obviously the size of the container is absolutely non-flexible. In fact, we only have a couple of sizes, but the big advantage is that you can put the same container on a lorry, on a train, on a ship, and use tools such as cranes and that kind of things to actually move containers. And this means that you don't really care about what there is into the container, but still you get, the ability of moving those kind of different kind of goods. So how this comes into IT containers, and why do we call them containers? So let's start talking a little bit about the containers advantages, or why should we be using containers instead of other kind of software packaging, because in the end of the day, the container is basically a software package system. So first of all, is less overhead. So the idea is that a lot of times the software gets shipped or thought about, or run into a production environment within some kind of, let's call them virtual machine. It could be a real virtual machine. It could be something like an LPAR, or any kind of virtual environment where an application can stand. And the characteristic of this is that obviously the reason why we want to have this kind of system is so that we are able to potentially move this application from place to place. So the advantage of having such a container is to increase the portability of that application. Now, talking about portability, it's a complex topic, because we can think about portability as for porting an application from one platform to the other. It could be porting an application from a physical mainframe to, let's say, a virtual mainframe, in the sense of a mainframe in the cloud. I know that for now it's not available for production use cases, but it might be at a certain point. But even if we are talking about a virtual mainframe for development purposes, it would make sense to be able to easily and quickly deploy something there, test it, and then deploy it on a production mainframe. But also can mean from the various stages of the application lifecycle. And this is due to the fact that we can have the same kind of operations done on this item, which basically we can think about this as a box where we put the application into it. No matter on the specific application that is in the box, we can use similar approaches to this. And a consequence of this is clearly a greater efficiency, because on one hand, obviously, we do have the the efficiency given by this consistent operations that we can run on those applications, but also the additional efficiency that we get if we consider a container instead of a full-blown VM or other kind of more heavy packaging. And then as the last point that containers, last advantage that container provide us is a better way of doing development. And by better way, I don't mean specifically better than the previous one, but I mean that it's more standard and we can leverage other kind of development best practices and resources, tools, and so on to effectively be able to develop containers and applications. So with those ideas, let's see a little bit a couple of use cases where containers are usually used or how they are usually used. So the first case is the lift and shift. So the idea is that you would start with whatever application that is running already on a platform. It could be x86, but it can be also mainframe power, whatever kind of architecture. And you simply put that same application into a container running on the same machine. So effectively, this allows you to have the advantages that we have discussed about container, but also not have to rewrite your application because the same application that was running outside a container will be able to run within a container. Now, there are a couple of exceptions because obviously there are a couple of trade-offs here, but usually an application can be very easily lifted and shifted into a container. Another approach to use container is refactoring existing application for containers. And this means that you start from your application that was already running on the machine, and maybe you do a little bit of splitting, or you maybe externalize a piece of this, a service, and maybe you don't try to put the whole application into containers, but maybe only some parts of the application into containers. So effectively, it's a way to improve a little bit the application, but without having too much work to do to rewrite maybe the application. And the third option is obviously for applications that have been designed for cloud native deployments, which means container deployments. And the idea about those kind of application is that they leverage all the features that we have seen from containers. And this also is a way of using containers and is to support microservices architectures. Now, I know that microservices are not usually foundable on mainframes, but as we will see, there is a lot of advantages of potentially co-locating some small applications or small APIs to the data that you already have on the mainframe or other system that you already have on the mainframe due to the latency that at that point you would not have on the conversation between the applications or the application and databases, as well as all the benefits that the mainframe clearly provides you. So another advantage or case where it would make sense to use a container is when you want or have to use a CI/CD system. The idea behind CI, which is continuous integration, and CD, which is continuous deployment, is to help the development of an application, ensuring that it's always properly working with the continuous integration, as well as that is easily deployable the new version with the continuously delivery model. And this allows you to develop application in a way more agile way. And the last container use cases that we'll be discussing is about providing easy way to create deployments of jobs and tasks. And the idea here is that a lot of times, also in the mainframe, you already have some systems to schedule jobs and handle those. But it might be that in the moment where you receive an application from other parts of the business, it's not written to be run on a mainframe, but it would still make sense to do data locality or other reasons. And if they give you a container, then it becomes way easier to handle than another kind of application where maybe you need to have more in-depth knowledge about the exact things that it is doing. So we have talked about container, and even though we have mentioned the fact that OpenShift is a container platform, it's a very specific kind of container platform, which is a Kubernetes container platform. So what is Kubernetes? Kubernetes is basically an orchestrator that orchestrates containers. And the reason for this is that sometimes you have very good hardware, such as mainframe hardware, and good applications which stay up, and everything is fine. But it does happen in the real world that you don't have maybe perfect hardware. So for instance, if you are on x86, that would be a case, or you simply have applications that are not that reliable or that might require some kind of management orchestration, or simply to help the scheduling in a more optimized way. So one thing that Kubernetes gives us is the service, the ability to, in one hand, do service discovery, and in the other, do load balancing. So the idea here is that you have different kind of constructs into Kubernetes, and some of those are clearly the application that we discussed into the containers and so on, and others are called services. And the way that services behave is fairly similar to providing a DNS or some kind of resolution to the containers themselves. So the advantage you might have is that you might have a service which would provide a name to your application, and then one or more containers that are effectively serving that application. And what will happen is that every time the service gets called, the request gets forwarded to one of the containers. This allows you first to be able to communicate with that application without having exact idea of the IP or the port, whatever that application talks on. And also the ability of having multiple instances of this application and be able to round robin between those instances. Obviously, only about the instances that are live, because in the moment that one of those instances will fail, it's removed from the pool, and therefore no additional traffic gets served to it. Now, the advantages of this model is that it allows you, if you have, for instance, multiple partitions or systems, to schedule some application to be run on multiple systems, and at that point, the traffic gets automatically load balanced across those. Another advantage that there is the storage orchestration, because if you have external storage, everything is, or provided storage, everything is easy, but there are some situations where you would need to have knowledge about the fact that a storage system is available or not available for a specific machine. And this allows you to ensures that an application only gets scheduled where the storage is available, because obviously if your application does require storage, it will not work properly if it's not able to access it. Another advantage of Kubernetes, and a feature I would say, that provides on top of containers is the application lifecycle. So effectively, what Kubernetes allows you to do is to have additional concepts on top of the application, which is the concept of deployment for complex application, if you will. And what this allows you is to either have multiple containers of the same application, in the sense that maybe you have an application that is 5 different components, and you want to be sure that those 5 components are always at the same version. Because if you have different versions, then you would have your application running effectively in an inconsistent way. And the way that you can do it with Kubernetes is basically you decide which strategy you want to use for the updates. And based on the strategy, you can, for instance, decide to do a blue-green deployment. So effectively, you have still all your old containers. You create a new set of containers with the new application version, and all the traffic is still sent to the old pod of containers, the old stack of containers. And as soon as the new stack of container gets released, get started and is properly functioning, then all the traffic gets rerouted. And this has multiple advantages, one of which is that from a specific moment in time, you will get old requests to the new version. Before that specific moment in time, all the requests were in the old version. But still, you have the ability eventually to fall back to the previous deployment if that is part of your deployment strategy. And other options are, for instance, to have a bunch of containers with, let's say, version A, and then you start deploying one additional container of version B, and you start to round robin traffic there. Maybe you move 5% of traffic. If that makes sense and is stable and nothing crashes, then you move more traffic from A to B, and at a certain point you will reduce the containers with version A and increase the containers of version B until obviously you don't have any containers with version A still available. So as you can see, it's very flexible way of thinking about application, because it decouples the content of the application, which is the application itself, from the way the application is effectively run and managed. Another advantage of Kubernetes is that due to the fact that it's able to schedule those containers on the machines that are offered to it, it's able to better utilize all the resources of the machines, because clearly it's like playing with small Lego bricks, and you can fit them a lot in a fixed size container. Another advantage is that Kubernetes is able to self-heal in the sense that if a container, for any reason, either due to the platform or the application itself, crashes, Kubernetes will restart it. So, or obviously, if it got set to do it, it's also possible to set it not to do it due to the application specific details or needs. But this is a capability that Kubernetes offers. And the idea with this is that, let's say if you have an application that is running with 3 replicas of the same API, and for some reason one of those crashes, obviously all the traffic will go to the other 2. In the meantime, Kubernetes will restart the third pod, third application, third instance of that application. And as soon as it's ready, then the traffic will be rerouted to that application as well. And the last advantage that we will be talking about in Kubernetes land is the fact that Kubernetes is able to handle configuration and secrets. So effectively, what you can do is inject either environment variables or files in specific location of your container. And as for the application point of view, those files or environment variable are always set, because every time the container will start, those uh, content will be populated as expected. Now, the advantage in Kubernetes way of handling this is that those are actually dynamically compiled, which means that you might want to have, for instance, 3 instances of the same application, but with a different configuration file. Let's say that you are serving a certain application for 2 different customers. One needs to have a certain configuration file because that is their configuration. Another one has a different one, and you can simply use the same container or the same application with simply just 2 different configuration files to handle those. And secrets is basically a way of creating those files from encrypted material, which would allow you to have higher security standard for your configuration. So I've mentioned a couple of times some Kubernetes names of things. Let's just quickly go through them to ensure that it's clear what exactly those are. So the first one is a container. A container, as we have seen, is where we would put our application, but we can define it in a different way, which is, I would say, the way I do prefer, which is the idea of a group of processes that have a limited access to the system based on their C groups. Now, as you might have imagined, we are talking about Linux containers. So effectively, what you would have on a mainframe is either a Linux One system or a Linux VM on top of the mainframe running those kind of things. Even though it's possible to do some more Z native thing with ZCX, but it's slightly different. But the basic idea is the same. So you would have those processes that actually think that they are the only one running on the system, because they are not able to see and interact with processes outside their set, but effectively they are not really. Container image is a tar file. That is a very basic way, I would say, to define it. But effectively, it's exactly what it is. And it contains everything that will need to be run. So what happens is that from an application point of view, they do see only one file system, which is the one that they are running on. The reality is that you would have a base file system, which is usually partially the host file system, partially a fake file system provided by the containerization system itself that gets overlaid by whatever you put into the container image. So from the application standpoint, it's just a normal file system, but in reality, it's a layer file system which allows you to place files exactly where you want them to be. A pod, which is the basic unit considered by Kubernetes, is a group of containers. And the reason why we have this idea of pod is because there are some cases where you want to have multiple containers and ensure that they are always scheduled on the same host. And this pod idea allows the scheduler to exactly know where to schedule things, and if 2 containers can be scheduled on 2 different hosts or they have to be scheduled on the same host. Service is what we were discussing before around the fact that we are able to do load balancing and service discovery. The component that allows you to do it is called service in Kubernetes. And persistent volume is the way that Kubernetes thinks about storage. So it's effectively a storage disk or a volume that the container can ask and can handle, but in reality is then provided by some system, could be a SAN, could be internal system into the machine that it's running on, or things like that. Config maps are the configurations that we have discussed before. It's called config maps in Kubernetes, and it's a way to set those files and environment variables. And secrets are the way to inject encrypted material into those config maps. So speaking about components a little bit, very quickly, the way it works, Kubernetes is fairly straightforward. So first of all, we do have an etcd, which is a database. It's a file storage database. And the idea is that you would have multiple instances of this, usually it's 3, and those gets synchronized within the database itself, and will allow you to have a consistent state of your pods, containers, services, and so on. Then you do have API servers, which is the Kubernetes control plane, which will, first of all, read and apply the state within etcd, and then will allow you to ask for a change of state to etcd. The control plane nodes are simply the nodes, VMs, whatever, that run etcd and the API server, and the worker nodes are the one that will run the workloads that effectively do the business value part of this. The infrastructure nodes are all the other kind of nodes that don't run worker nodes, workloads, but also don't run etcd or the API server, which, for instance, could be some kind of networking adapter or storage adapters or things like that. So why is this important? The reason is that the public cloud and multi-clouds are now becoming the norm. And my belief is that they will also arrive to a level of multi-architecture, including the mainframes. And if we look at numbers, 95% of enterprises will be using a mix of cloud models in IDC Cloud Forecast study. 31% of all compute capacity will be in private or premise cloud in 2 years, which is, I would say, lower than the current one, because I think now we are in the 50s, 60%. But if you think about how much it will increase the overall quantity, obviously the on-premise part will not diminish, but it will probably grow less than the public part. And 60% of enterprises will use some flexible consumption model by 2023. The prediction was made, I think, in 2021. So we'll see if this becomes a reality very soon. But the idea is that even though for a lot of kind of workloads, it does make sense to own machines and have CapEx expenditures around this, it does not make sense for other kind of applications that might be running in business. So how exactly OpenShift helps you with this? The thing is that you would have OpenShift that can run everywhere. And by everywhere, I mean that it can run obviously on mainframes, it can run on Power, it can run on x86, on ARM, and those can be real machines, virtual machines, private cloud, whatever that means in your company, or public cloud, or potentially even edge devices, which we define as edge as everything that is not in a data center. And since OpenShift can run on all of those, your application can run just on OpenShift and not be aware on exactly where they are running. Now, obviously, there are a couple of asterisks here and there because, for instance, in the moment where you want to run the same application on x86 and S390, you will have to have two compiled images of these, two container images of those applications. because clearly you will want to have a compiled S390 version of it and a compiled x86 version of this, because of the different architectures, it's different images on for compiled applications. If your application would be purely interpreted, then you would not have this issue. You would have a single container image that does not require any specific architecture, and therefore you can deploy it everywhere. But clearly, if you want to create something that is multi-architecture, you will have to provide probably some ways to produce images in a serial way for all your supported architectures. But except for this small detail that still get managed at runtime by Kubernetes itself, you don't need to do any specific Kubernetes configuration to tell it, this is an S390 machine, run an S390 image, because Kubernetes will self-detect this. It will just need to be available to Kubernetes both image one per architecture. And from the application standpoint, it will not feel the difference between any kind of platform. So OpenShift is actually more than this, because we also have a lot of products around multi-cluster management, cluster security, or registries and other things that help to create a full architecture. But I would say those are outside the scope of the current conversation. So I think the big question that everyone has is, how does this work with the mainframe? And my feeling, and this is what I've been saying for probably more than a year now, is that I don't think that containers will displace the mainframe. I think that they will enhance it. And the reason for this is that there are a lot of features that are working well in container land that maybe can be improved into the mainframe one, and vice versa. So let's see a little bit whether that OpenShift on the mainframe actually makes sense. So the first one is the development consistency. So when you are able to deploy containers on the mainframe and x86 or whatever other systems get used in your business, this allows you to have similar processes and tools for x86 machines as well as mainframes. And this allows you to create a lot of shared knowledge between those teams and people. Another big advantage is that mainframe compared to the whole IT is just a small part. And by being able to use similar tools than non-mainframe deployments, you get all the knowledge of those and tools as well of all those people and experience that is there. Obviously, mainframes are not x86 machines, so I am not trying to say that you can move all the knowledge from here to there, but still you can learn stuff from there, and obviously they can also learn things from mainframe experience. Then, as we discussed, there is the advantage of the workload portability with the asterisk of the compiled part. But at runtime or application from the application point of view, the workload becomes way more portable. And why the mainframe under OpenShift? So why should you be running OpenShift on a mainframe instead of on an x86 box? So I would say the first reason is data gravity, because obviously you would have already a lot of data or application services, whatever, running on the mainframe. And if you can also run your new application on it, that will give you very good latency, and bandwidth and throughput. Another advantage is the low latency, which obviously is something that it's very difficult to have if you have multiple systems, one with your application on x86 and the other one with the mainframe and data. So putting all together will mean lower latency. Another advantage is the consolidation and TCO reduction. So I have seen and done some calculation myself, and I think that in a lot of cases, the same application running on in a container can be more cheap to be run on a mainframe. I'm not saying about the hardware itself, obviously, but the total cost. So I think that should be an aspect to be considerable. Another advantage is the business continuity. So in x86 land, you would have machines, so you would have a cluster that would contain multiple physical machines, and some of those machines might fail, and at that point the workload gets rescheduled on a new or a free system, and everything restarts again. With the mainframe, you have the advantage that that does not really happen, because you are not losing resources. Or, I mean, you might be losing resources, but you are not losing a mainframe, a full mainframe, or a machine running on it. So effectively, this would allow Kubernetes not to have to think too much about rescheduling jobs that fail due to hardware failure, and this would guarantee a higher throughput and more continuous throughput, even in case of hardware failure or other kind of failures. And the other big advantage is the fact that if you're running on a mainframe, but I would say on every platform, you can still leverage some aspects of the platform you're running on. So my point is that containers are an abstraction in a way of the underneath hardware, but at the same time, they are kind of a leaky abstraction, because they will take advantage, as we will see, from whatever hardware acceleration and features the system has. Obviously, a good application will be able to run on multiple kind of hardware, but run maybe in a better way on a specific kind of hardware, and still be able to run on other kind of hardware that maybe don't have that specific feature. So I'd like to have a very little discussion about HA and DR, so high availability and disaster recovery on OpenShift and mainframe. So OpenShift only handles pod failures, node failures, in the sense that if a whole box goes down, it's not handled by OpenShift itself, because the idea is that there will be a human that will fix it. Obviously, the application that we're running on that machine will get rescheduled on a different machine, but the machine will not be part of OpenShift or Kubernetes interest. And second is that, as we have seen, that we have this etcd, which is the storage behind that keeps the state, that is usually scheduled in 3 drives. Effectively, we have 3 instances of those. And the reason why we have 3 is that we need, there is an election model within etcd, where basically, as long as there are 50% plus 1 of the replicas that are running, everything works. If you go below 50% plus 1, it will go in read-only and potentially crash completely at a certain point. So it's very important for Kubernetes itself or OpenShift to have those etcds properly running. And if you think about the mainframe is very good at keeping things running, so it could be a very good choice to have those etcds. It would be a very big advantage of having them on the mainframe. And even though it's possible to have RTO 0 or RPO 0, it's very hard to have it on a software-defined storage. While on a more hardware kind of solution, it's obviously easier. And as we know, the mainframe has capabilities of keeping up services, and with the possible storage solution that there are with the mainframe, you can have very good RTOs, RPOs. And all of this can be tweaked for different kind of usages. Now, there is also another feature that it's very interesting and is coming, in the sense that now it's some kind of technology preview. So effectively you can use it, but it's not supported yet, but it will be soon, that has a cluster, like an OpenShift cluster, running on non-homogeneous kind of architecture of hardware. So effectively what you could have is potentially some so etcds, so the control plane running on a mainframe, and then the worker nodes running partially on a mainframe, partially on outside the mainframe, maybe on x86 or whatever other system. And the advantage of this is that you would still have all the advantages of having the control plane on the mainframe, and maybe some application that prefer the stability that the mainframe can provide, while other applications that maybe have different kind of needs can run on different kind of hardware. And that would allow you to have even more flexibility on exactly what kind of hardware you want your application to be running on. So speaking about specific advantages or capabilities that the mainframe hardware can give to a container, is the Crypto Express card performances. So effectively, if you're running OpenShift or Kubernetes on the mainframe, and a container needs to do a lot of crypto operation, it will be the application will use the container virtual system, but the container virtual system will not perform any operation and forward the operation to the hardware, to whatever layer there is below it, and eventually it will arrive to the hardware itself that has all the accelerators, and therefore will have a very good throughput. Another advantage is obviously that the latest version of Crypto Express also has quantum safe algorithms, ciphers, and so on, which allows you to effectively have all those things available in your container, from usable by your application that is running within the container. And if you have created your application in a sensible way, or the container with additional services in a sensible way, what you would have is that the same container, if run on a mainframe, it would use all those features, while if it's not running on the mainframe, it would use some different kind of implementation, so that effectively it still has the feature, but also not the same speed. And the way that you can do this with OpenShift is with the device plugin. So what you have in OpenShift are those containers that you can use to be in the same pod as your application, and effectively those will provide additional services to your application. And one of those can be the CEX device plugin, that will allow you to use all those crypto express features. So wrapping up, I think there are a few points to make. The first one is that it's very important nowadays to have more portable application. That does not mean that you need to port your application on the mainframe or outside the mainframe, but just to be able to bring them between different mainframes or different environments would be still a big advantage. Obviously, then you can also do bigger changes, but that is not the only point of portability. Second, containers and their baggage can bring new tools to the mainframe development, which can help modernizing the way some processes are done or some development are done on the mainframe architecture. And the mainframe is a great platform to run containerized workloads as well as non-containerized workloads as well, obviously. But also containers would run very well, I think, in mainframe. And last point is that OpenShift enables application to be uncoupled, decoupled from the hardware itself, and this gives a lot of flexibility, but also it allows the application to still leverage platform-specific optimizations. So with this, thank you. And there is the feedback form as well. I don't know if there are questions as well. I don't see any in chats, but.
That was a great presentation. Thank you very much. We've got plenty of time for any questions for Farley. So if anybody wants to type in the chat, we can get them questions answered. And while I wait for any questions in chat, if everyone would be able to fill out the feedback form that I've put in the chat, that'd be much appreciated. And thank you for presenting, Farley. It was really good.
Thank you.
We'll just wait a few moments to see if there's any questions. It looks like we're all good. Oh, there we go. Thank you for your presentation, says Adrian.
Thank you.
Okay, so thank you very much for presenting, and we will leave it there.